So today we're going to be looking at EFX and M allocations in fair division. So specifically, we're going to look at the question of distributing indivisible goods to a set of agents in some fair manner. And it's a common question in economics, computer science, and algorithmic game theory. And we're going to look at two prominent fairness criteria, namely one of them being MB fairness up to any item, or EFX, which essentially tries to minimize the MB between any two players and maybe saying, okay, even if I MB you, if I take away any of your items, I won't MB you anymore. And we're also going to be looking at the maximum allocation. And in this case, it's just trying to maximize the minimum utility of all agents. We're going to normalize our utility functions because this doesn't affect MB, but it does affect maximize and provides a lot more interesting results. So specifically, our objective for this project is to explore the tension between EFX and MM. And we want to found counterexamples or to build a system to explore the types of counterexamples and utility matrices. We want to be able to characterize these counterexamples all under one bundle. And we want to see if this approach can also hold for stricter claims. For example, when all agents have the same item rankings, maybe this is a guarantee or this is not a guarantee. Then we want to see how far away these MM allocations are from their EFX counterparts and see if there's ways to get from one to another to ultimately answer the question of does EFX always exist, period. So our methodology is to use an evolutionary search, where essentially we will generate a population of a lot of random utility matrices. And then for each matrix, we're going to see the MM allocation and see if it's EFX. We'll keep the fittest ones, the ones that are most likely to be counterexamples. And then we'll take parts of these fit matrices and essentially evolve them to create more likely counterexamples. And then after we do this, we'll also analyze how far away for each matrix their MM allocation is from any given EFX allocation. Specifically, we looked at swap distance, and this is our main comparison, but we also considered other metrics. So for our results, well, the most important thing was, yes, we did find counterexamples to the MMEFX problem. We're pretty lucky that our evolutionary search was successful. And we also use this same approach to find counterexamples to specific utility matrices where the item rankings are the same, which all of this will make more sense when I go into the examples later. And after we found counterexamples, we also found some way to kind of structure them together. And because most of them had the same qualities of having competitive goods and spiky preferences. So to answer the original question, no, there does not exist always an allocation that is EFX and MM given some utility matrix. So to look at one of our first examples of a counterexample, we can see here that agent A values these items at these preferences, same with B and C. And we can see in our MM allocation, our maximum minimum is 30.94%. That's the minimum percentage or the maximum percentage we can guarantee for all three agents. And our best EFX allocation is 22.30% of total utility, which means out of all possible EFX allocations, this is the one that's the best in terms of making sure everybody gets at least some portion of what they want. And our important things to look at in terms of our counterexample matrix is that the agent A and B both have pretty spiky preferences. They both like item one a lot more than the rest of their items. And there's also a very competitive item, which is item one. And this was something that was very common in every single counterexample we had. And it's also really interesting to look at the distance between this MM and EFX allocation, because all we need to do is for agent A to give item three to agent C, and then we see that we have an EFX allocation in this case. And in this example here, we see a lot of different things. So in this case, every agent has the same ranking of items. Specifically for here, it means every agent prefers the ninth item more than the eighth, seventh. We can do this without loss of generality. It doesn't really matter what order they are. But this is a little more interesting because while there is a spiky preference for C, we can see that it's a lot less obvious compared to the last one. So maybe we should focus a little more on this rather than the competitive nature of items, because here we can see that every item is pretty competitive for all of the agents. So maybe it's not a great way to just say competitive items will have an effect. And it's also important to realize that while counterexamples may have these properties, it doesn't necessarily guarantee that if you have these properties, you're a counterexample. It's also a little weird to look at the MM allocation and the best EFX allocation in this case because there's no real clear way to go from here to here, although they share some similarities. But with that said, we've done more research and we can see that or it's not shown here, but there are EFX allocations that are a lot closer to the MM allocation, usually within one or two swaps. So we can also see that for our counterexamples, they perform a lot better in our score test compared to these artificially generated ones. We tried to replicate our counterexamples by looking at agents with specialized preferences or spiky preferences. We looked at competitive items. We looked at having poison items or ones that no one really wanted. And we also looked at just random matrices in general. And we can see that counterexamples did perform a lot better than the ones we tried to artificially generate that were not counterexamples. So what are our main conclusions? Well, our work says that while for most matrices, the MM allocation is usually EFX. This is not really a sufficient condition. This is not true for all matrices. And we can see that evolutionary search is very effective in finding these counterexamples and that most of them have some way to classify, although this is still to be researched. And a lot of future steps, well, the first thing that comes to mind is reinforcement learning instead of evolutionary search. And since we already have a data set of all these popular or actual counterexamples, we can use it to train a model to hopefully find some better ones for more agents or more items. And we can also look at repair items to go from MM allocation to EFX allocation, since we've shown that for all the counterexamples, it's pretty close to some EFX allocation, although it might not be the best one. And we can also update our scores to better encapsulate the more modern counterexamples we found in this problem. Thank you guys.